Hey everybody, so we're going to continue talking about moments and centers of mass and these things. On the left-hand side here, I've got some of what we've developed already. We looked at a system of masses in the plane. We started with a system of masses on a single line, and now we've extended it to the plane, and we have these this big concept of center of mass built out of these other concepts. The moment, we have a moment with respect to the x-axis, and the moment with respect to the y-axis. They're just the sums of the masses times their distance from the respective axes. And then the center of mass, the coordinates are given by dividing those moments by the total mass. Okay, so we're going to use this, right? That's what little m is there, is the total mass. Our goal here, we're going to use this, is what we've been building for, to get to a place where we can, so imagine, I don't like how that looks. Imagine we have a what we call a lamina. It's, let's think of it as like a flat, some kind of flat arbitrary shape. Its density is going to be consistent throughout, so there's going to be no changing density function like we saw in some of the earlier videos. And by flat, we're just gonna essentially we're gonna ignore that it's a three-dimensional object and say that it's so flat that we can treat it like a two-dimensional object. And what we're looking for is a point in this object where, if we had a little cone or something and set it right at that point, it would balance the object, right? We'll call this the center of mass of this object. So let's start with a little bit of vocabulary, and then we will we'll move into how we actually do this. So we've already talked a little bit. We're talking this thin plate. We will sometimes call a lamina. I'm fine with either term. I just want you to know, because you might see that term out there in the world. Same thing with center of mass. This is a perfectly fine term, but you also will hear it referred to as the centroid. And we're going to use something now that I'm going to present without proof. This, I think, will be pretty easy to conceptualize, and it matches pretty well with our intention, our intuition. We're going to be using something called the symmetry principle. And all this says is that if a region R is symmetric about an axis or a line, let's say a line L, then the centroid, or the center of mass, lies on L, right? So for instance, if we had a region that was shaped like a heart, I think if you imagine that I drew this perfectly, we can see that down this pretend straight line, the heart is symmetric about that, right? You can reflect it over that line and you get the same shape. What we know from the symmetry principle is that wherever the centroid is, it lies on that line, right? I don't know how far up or down the line is, but I know it's gonna be right in the middle, the horizontal middle of that heart, right on that line, right? If you have a shape like a circle, right? It's pretty easy to see that a circle is symmetric. Again, we have to pretend that I've actually accomplished drawing these. Let's see if this works. There we go. That's a little closer to the center, right? So the circle is symmetric over both of these lines. And you could draw an infinite number of lines that it's symmetric over at all different angles. But all of them will pass through the center of the circle. And since by the symmetry principle, the center of mass has to lie on any line that has a symmetry for the circle, which is going to be all lines through the center, then that center point that they all pass through is the point where the centroid is, which I think is what we all imagine. If you were trying to balance a plate on your finger, you'd put your finger in the middle. And we don't have to think too hard about that. All right, one more piece I want to throw at us, just reminding us of a couple of ideas we've seen previously. The idea of a moment for some object is its mass times the distance. So the distance here is the relevant distance. If we're doing a moment around the x-axis, it's the distance from the x-axis. If we're doing a moment around the y-axis, it's the distance from the y-axis. So whatever the relevant distance is the distance I'm talking about there. And I want to remind us that mass we can think of as density, and we've used this Greek letter rho to signify density, times, and let's come back to this, we'll still have distance out here. So what goes in those parentheses, so in previous videos we've done a linear density function. We imagined rods that had a density that changed over the length of the rod. Well, then we'd put in the mass times, to get the mass, we'd take density times how long the rod was. Here we're talking about shapes that have area, and so we'll have density that's going to be mass per unit area, so we have to take that density and multiply it by area. Okay, so this is how we're going to get these moments in a moment. I will also note right now that the densities that we are going to be talking about, these laminas, we are going to assume that they're constant, right? We've done problems with linear densities that were changing. We're not going to have changing densities. And what we'll find out is that whatever this constant density is will end up canceling out in our computation, so it won't really matter much to us. But it's a good thing to remember that it was there, because you can have situations where it's not constant. We won't see that in this series of videos, but it is reasonable to have some kind of plate that's more dense in some areas than others, and then you can have a density function that tells you how it changes in each area. Okay, so that's the setup. Let's move into developing a way to come up with the center of mass for a lamina. So we're going to start with a simple lamina, and by that I mean its shape can be defined by a single function over an interval. So here I've just drawn an arbitrary function f of x from a to b. And so the lamina we're interested in is the lamina defined by f of x, the area between it and the x-axis, and then these lines at x equals a and x equals b on either side. So if you imagine that thing as like some kind of plate, and we want to find the center of mass for this thing. So what we're going to do is what we always do. We're going to break this thing down into simple parts, and then to get an approximation, and then make our approximation more precise with a limit, which we've seen over and over again leads us to an integral. So in this case, I'm going to think of this, instead of thinking of this lamina as this one complicated object with this weird shape that I don't know how to deal with, and think of it as a collection of masses, right? So remember, just a moment ago, we were looking at what we did last time. We knew how to find the center of mass for a system of masses in the plane. We have several point masses. Well, we're going to imagine this shape as being built up by a system of masses, and use what we did last time to find the center of mass of that system. It'll be an approximation because this is one object, but then we can take limits and make our approximation precise. So as usual, I've taken the interval a to b and knocked it up, chopped it up into subintervals, right? So I've drawn a certain number here, but just think of this as some arbitrary number. Let's look at one interval in particular. So first of all, as usual, I don't want to write everything down because this will become very cluttered, but this would be a, we might note these x values of the interval as x0, x1, x2, all the way on up to xn. If I pick some interval in the middle here, I might have x I minus 1 and x sub I. And we're going to look at this particular interval. We'll also have our usual notation. The difference between each of these x values is delta x. Okay. So the way that we're going to chop this lamina up is also something that is probably unsurprising. We're going to use rectangles. So again, we can imagine drawing rectangles from each interval. I'm just going to draw this one. And in this case, our rectangles are going to go, we're going to use the midpoint. I'll have to adjust this. This is not looking great. Oops. Let's try that again. So we're going to use the midpoint of the rectangle to determine the height. Okay. So let me make a quick adjustment. Huh, I thought there was a way to do this. Well, in any event, we can estimate here. Okay, so there's our rectangle, and we've used the midpoint. I've tried to get that about right to determine how high it is. That will come into play in just a moment. So I'm going to take this rectangle and move it out here. So imagine this is the same rectangle. I just want to draw it. I'm exaggerating the width to make it easier to draw things. There's our rectangle. Okay. Now, remember this side of the rectangle was x sub I minus 1. This side was x sub I. And we used the midpoint. I'm going to call that x sub I star to determine the height. Okay, I'm just naming things here. So, sorry, I want to use a different notation. I'm going to, instead of x sub I star, let's use a more standard notation. X sub I bar. This is a typical notation for this. In this case, x sub I bar is the mean of those two x values on the left and the right, the one right in the middle. Okay. Now, remember, we're imagining that this lamina created by a function is built of a bunch of individual masses. Each of these rectangles is going to be our individual mass. We need to find the center of mass of each of these to then determine the moments for this piece of the lamina. Well, where's the center of mass of this rectangle? We just talked about the symmetry principle a moment ago. This rectangle is symmetric over a line cutting it in half horizontally and a line cutting it in half vertically. So its center of mass must lie on these two lines right in the center of the of this rectangle. Well, what is the coordinates of that? It's this midpoint for our x coordinate. What is the y coordinate? Well, it's half the height of the function. The height of the function, remember we chose the height of this rectangle based on the midpoint. The height of the function at the midpoint is just what this means, the height of the function at the midpoint, the value, and we just want half of it. So there's the coordinates for the center of mass of this piece of our lamina. Okay. What about the mass of each piece? Well, the mass, remember, is the density times the area. Well, area in this case, we take a rectangle's area is the height of it, in this case, the function at x bar sub I, times the width, which we, as usual, call delta x. And so there is a little formula for the mass. Okay. All right. So let's figure out the moment for each rectangle. So for rectangle, I'll call it rectangle R sub I. We're going to have the following. We have the moment with respect to the y-axis, and I'm going to add to this notation, just meaning for this particular rectangle. We're going to have lots of moments. There's the moment for this particular rectangle, for any other particular rectangle, and then we're going to have a moment for the whole thing. So I want to make sure I know which one I'm talking about. So the moment with respect to the y-axis for this rectangle is going to be the mass times, remember, the distance, in this case, from the y-axis. Okay, so we just figured out what the mass of this rectangle is. It's rho times f of x bar sub I delta x. Its distance from the y-axis, the distance we use is the distance of the center of mass, right? This was one of the notions we had in an earlier video. One way to think about the center of mass is it's the place where if you concentrated all the mass of this object, its moment would be the same. So when we figure out this moment, we can pretend like all the mass is concentrated at that center of mass. So the distance from the y-axis is just the x-coordinate, right? It's distance from the y-axis. So I'll draw it on here. Right, there's its distance from the y-axis. Later we'll do its distance from the x-axis. So this distance is the x-coordinate. The vertical distance is the y-coordinate. So in this case, that is going to be x bar sub I. Right? And just to make things more typical, I'm just going to reorganize. These are all factors. Everything's being multiplied. So I can reorder everything into a more, I don't know, traditional order. And there's our moment for the rectangle, okay, for the y, relative to the y-axis. We do the same thing for the x-axis, right? We're going to have the mass. It's going to be exactly the same, f of the density times the area. But now we need the distance to the x-axis, which again is just the y-coordinate. That's what that y-coordinate measures, the vertical distance from the x-axis. And that is 1/2 f of x bar sub I. Let's again put it into a more pleasing arrangement. The moment with respect to the x-axis of this thing is going to be 1/2 rho times, we've got f of x bar sub I squared delta x. There is our moment with respect to the x-axis. Okay, so oops, didn't want me to do that. Okay, there we go. Now we got another one. I'll leave these two things up here. So now you can probably guess what we're going to do next. We're going to add up the moments for the entire lamina, right? So I've drawn one rectangle here, but if you imagine all the rectangles next to it, we would figure out their moments, their individual moments exactly the same. And what we would get is that the moment, sorry, I'll try to stop moving this up and down. The moment with respect to the y-axis, this is now for the entire lamina, is going to be approximately the sum. I goes from 1 to n, and I'm just going to add up the moment for each rectangle. So in this case, that's rho x bar sub I f of x bar sub I delta x. And the moment with respect to the x-axis is the same idea. This is the approximation. We have 1/2 rho f of x sub I, x bar sub I squared delta x. And then how do we make these numbers precise? Well, we take a limit. We take smaller and smaller intervals. So we'll get that my is going to be equal to the limit as n goes to infinity of this summation, which we recognize now as being able to be written as an integral. And so the integral looks like this rho is a constant, and it's usually taken out front. We'll have the integral from a to b of x, f of x, dx. And then we'll do a similar thing over here. My is equal to the limit as n goes to infinity of this whole sum, I equals 1 to n, 1/2 rho f of x bar sub I squared delta x, which becomes, oops, I'm writing y, these are both x. Sub x. This becomes, again, I can take my constants out front. So I'll have 1/2 rho integral from a to b f of x squared dx. And there are two formulas for the moments of a lamina as described above, right? So this is a lamina where it's a single function and it's the space between the function and the x-axis on this interval. All right, let's add one piece to this. We want the total mass. So remember the total mass is, we use a little m, is going to be the density times the area. So in this case, that's rho. Well, the area we know is just the integral of f of x over that interval, okay? So there's our mass. So let's put this all together, and what does this mean? Well, what we typically write is that the centroid x, y is given by, x bar and y bar is given by, so x bar is going to be my over m, and y bar is going to be mx over m. Okay. Now, this is a perfectly good, and this is typically how we write it down. It's a nice, easy way to remember. It's exactly what we got when we looked at, whoops, I don't want that there. All right, this is looking too, I'll just do, okay. And this is great. This is a perfectly good, this is the correct formula. I just want to notice something that happens. Let's just look at my, for instance. If we were to compute this for some function, let's look at x bar. If we were to compute this, we look at my, which is rho times x, f of x dx. And we're dividing it by the mass, which is going to be rho a, b, f of x dx. Notice that rho cancels, it's a constant. We're in the situation where it's a constant function, and so it can it slips out of the integral, and we can cancel it in this case. And so sometimes you might see x bar written as, well, look at the denominator here. That's just the integral, it's the area. So we might write 1 over the area, and then we have the integral from a to b x f of x dx. And in a similar way, you've got a rho in the in this computation for y bar in the numerator and the denominator, and so you end up with just 1 over the area times 1/2 the integral from a to b of f of x squared dx. And so this is often how we'll end up actually computing them because of the canceling rho values. This works when rho is constant, and so that it can slip outside of the integral and be canceled out. Okay, last thing for this video, let's do one example using these two notions, these moments, and find the centroid. So let's find the centroid. For, what did I have? Y equals square root of 9 minus x squared. Sorry, let me say this a little more precisely. I want to do for the region enclosed by y equals 9 minus x squared, x equals 0, y equals 0, and for x greater than 0. Okay. So let's just first graph our region. So we want a couple of axes. We're looking in the first quadrant. My function's positive, and I'm looking at positive x values. So if you recognize this, right, you can take this equation and rewrite it as y squared plus x squared equals 9. We're looking at the top half of a circle. In fact, we're looking at the upper right quarter of a circle with radius 3. So my picture is something like this: 0, 3, 3, 0. Okay. And we want to find the centroid of this object. Okay. I always like to estimate things when I can, right? If I imagine this is a square, right? This circle would fit in a square with side lengths 3. The centroid would be right in the middle of that square by the symmetry principle. We've chopped off some of that upper corner, so the centroid should move towards the bottom. There's less stuff out there to be balanced out. So my centroid should be somewhere. The center of this square would be 3 halves, 3 halves. It has to be somewhere with a smaller x and y coordinate. That's what my intuition tells me, and I'll use this to judge my answer. It also seems, because the circle is perfectly symmetric, the x and y values behave identically, it should be the same coordinate for each. We're going to compute each individually, but they should turn out to be the same. So let's see what happens. Notice I haven't given you a density in this problem. And this is what we saw before is exactly why. Because the density cancels out, we can assume that it's just, whatever the density is, it won't change how this works out. And so if we feel insistent on writing the density down, we can say it's 1 unit mass per unit area. But I'm just going to not use it because it will cancel out in any way. So we want to compute, we need to compute a few things. We need to compute the area. So remember, maybe I'll write this down first. We want to find x bar, which is 1 over the area times, we have the integral. It'll be from 0 to 3. That's our region. X bar is given by x f of x dx. And y bar is going to be 1 over 2 area 0 to 3 f of x squared dx. Okay, so that's what we have to figure out, all these little pieces. So let's start by figuring out the area. The area we could figure out with an integral, 0 to 3 of this function, 9 minus x squared. But we know, we could take an antiderivative and work through that problem, but we know that this is a quarter of a circle. So it is going to be 1/4. This is a circle with a radius of 3. So the area is 9/4 pi. Okay, so there's our area. Now we've got to figure out these other two integrals. So let's go ahead and do that. So let's figure out, we'll do x bar first. We need the integral from 0 to 3 of x, f of x dx, which is the integral from 0 to 3 of x times the square root of 9 minus x squared dx. This looks like a u sub will work nicely. I'm going to take u to be 9 minus x squared. This will give me du is equal to negative 2x dx. I'm going to take the negative 2 over here as a negative 1/2. And I have my substitution. So this will be, we'll have, oops, let me give myself a little space. I like to take my constants out front, negative 1/2. Square root of u, and the x dx has been replaced by the negative 1/2 du. Let's look at our endpoints. When x equals 0, u is equal to 9. And when x equals 3, u is equal to 0. Okay, so let's take our antiderivative. I've still got a negative 1/2. The antiderivative, the power goes up by 1, but we get the reciprocal of that power right here, and we're evaluating it from 9 to 0. So I've now got 1/2, negative 1/2. I'll have 2/3 times, when we put in 0, we get 0. When we put in 9, 9 to the 3/2 is 27. So I get negative 1/2 times 2/3 times negative 27 is negative 18, or 9. All right, so there is the integral for the x bar. Let's go ahead and figure out the one for y bar. This is a bit easier. We'll have 0 to 3. We need f of x squared, so we just get 9 minus x squared dx. This is going to be 9x minus 1/3. Oh, I see. 9x minus 1/3. I was wondering what happened to my factor of 1/2 from our formula, but I left it up there. 1/3 x cubed evaluated from 0 to 3. This is 9 times 3 minus 1/3 times 3 cubed, which is 27. This whole thing looks like it's going to be, oh, sorry, I'm doing this wrong in my head. 1/3 times 27 is 9, not 18. I was wondering why this wasn't working out. So we get 27 minus 9, which gives us 18. Okay, so now let's bring these back up here. So we have these two numbers, 9 and 18, for the integrals here and here. So x bar is equal to 1 over a. So in this case, a is, let's just write this as 9 pi over 4. So 1 over a is going to be 4 over 9 pi. So 1 over a, 4 over 9 pi times 9, or 4 over pi. And we've got the same thing here, except 1 over 2a. So that means we have, if we multiply the denominator by 2, we will have 1 over 18 pi times 18 gives us, oops, I forgot my 4. 4 over 18 pi times 18 gives me 4 over pi. And so as we thought, they were symmetric. So the centroid is then at 4 over pi, 4 over pi, which we predicted it would be symmetric. As a decimal, this is like 4/3. It's a little bit smaller than 4/3. So that's like let's estimate it at like 1/4 is 1.3 repeater. So I'm going to estimate it at about 1.2, 1.2, which is also what we said. It would be slightly closer, right? We've made 1.5 and 1.5 the center of that square we imagined. We've made the coordinates slightly smaller. Okay, so it fits in with our guess at the beginning. So it tells me if we made some errors, they weren't massive. You know, these estimates can never tell you you're correct, but they can definitely tell you when you're wrong. Okay, so that is it. There's a lot of steps to these, but it is just following a formula that we gave up here. All right, that's it. I will see you next time.